Good morning, class. Today we will be discussing some concepts on reinforced concrete columns. So we start first with actually loaded columns. Okay, actually loaded columns or concrete columns are those columns uh, in which the line of action of the force is actually concentric, which means that it passes through the longitudinal axis of the member. So if we have here a column section, and if we define this as your longitudinal axis, so the force is actually coincidental with this axis that passes at the uh, center of gravity of the concrete section. So your P here is actually an actual load. Okay, so if we look into the section on top view, supposing this is your okay, section, so this is the center of gravity of your uh, column section, your P actually passes right through this point. Okay, so this is what you call an actually loaded concrete column. And the implication of such is that your columns have zero eccentricity. Okay, so the actual load P passes uh, right at the point where this longitudinal axis is located, and therefore the eccentricity is said to be zero. Another implication is that for actually loaded columns, we say that there exists no bending. Okay, so the column remains straight because there is no tendency for the column to bend. Except, of course, when we study some buckling concepts, which is not yet a part of what we are discussing right now. Okay, so there are some types of columns according to the way the reinforcement are placed. You call this now the first one a tight column. Okay, so a tight column consists of reinforcement that are tied together by what you call lateral ties. Okay, so this is now your lateral ties. We call this a lateral tie. It's like a stirrup, but it looks like a stirrup, but it does not function only as a stirrup. It functions more than a stirrup. In fact, the word lateral means that the column is confined in some uh, degree to avoid what? instability on the particles. Okay, so the confinement there actually uh, uh, make your concrete um, stronger in terms of bursting. Okay, so if you have a good confinement, a lateral confinement, then your column will behave much more stronger. Okay, so we will dig deeper into that scenario when we go through the lecture. So for the formula of tight columns, this now the equation that we need. Okay, so this equation is simply stress. Okay, so Pu or P is simply a stress multiplied by the area. Okay, so you have here a stress and an area. You have here a stress and an area. Okay, it consists of the concrete part, which is this one, and the steel reinforcement. And these are factors that we normally consider for what? For safety considerations. Okay, so phi is the reduction factor. It's called a reduction factor. And 0.8 is called an efficiency factor. Okay, so how efficient the tight columns are gives you this 80%. Okay, so we can conclude that tight columns are 80% efficient, and the reduction of phi gives us additional factor of safety. What again is the factor of safety of phi? So it is actually due to some errors in uh, the actual implementation of your uh, design, which can be attributed to dimension errors. Okay, can also be attributed to errors on calculations, etc. So the reduction factor actually is a combination of a lot of errors brought about by the design and the construction of your column. Okay, so for the vertical spacing of the lateral ties, so when you say vertical spacing of the lateral ties, if these are your ties here, so if I draw now my column uh, reinforcement, so my lateral ties are actually spaced, okay, in such a manner that it will give enough confinement on the concrete poured into it. Okay, so if I have concrete poured here, these lateral ties will act as confining reinforcement, not only shear reinforcement, but also it acts as a confinement for the particles. So the particles of the concrete here inside, this confinement will not easily get out of it. Okay, so that's why we need to take note of this code provisions to address, okay, the concern regarding confinement. And the vertical spacing, we call this the vertical spacing because this is a vertical view of your column. So these are now the vertical spacing S, okay. It can be uniform, it can be non-uniform depending upon the purpose and the design. So the code provision on the determination of this vertical spacing is given by three uh, expressions. The first one is 48 tie diameter. So T there refers to your tie diameter, okay? (16 bar diameter, so your dB there refers to your bar diameter, the main bar. And the least dimension of the column. So remember that for a rectangular column, the least dimension is uh, maybe, okay, may be attributed to this or this, okay, whichever is lesser. Okay, take note that B is not less than H always, okay, and H is also not greater than B always. So the B and the H then will actually be dependent on the bending of your column. But here, in actually loaded column, we don't have to worry about B and H yet because there is no bending. Okay? So I will explain to you further how to distinguish B and H when we go to bending of columns. So it's no longer an actually loaded column. So in these three code expressions or code requirement, we choose the smallest. Okay, for safety reasons and conservative design, we choose the smallest. And the minimum clear cover over the tie wire. Okay, so where's the minimum clear cover? Okay, if I have here my column, and this is actually the outer surface of my concrete, okay, my concrete column. So the clear cover that I'm referring to here is simply this distance, okay? So from the surface, outer surface of your stirrup up to the concrete surface, you call this now the clear cover or the CC. And CC is simply a comparison again of three expressions, which is 40 millimeter, bar diameter, and 4/3 the aggregate size. Okay? So if I have these values, I simply choose what? You say minimum. Will you choose the smallest or the largest? Okay, so we have to choose the largest. Okay, it's the minimum required. So here we choose the smallest, but here we choose the biggest. Okay. Okay, for the clear spacing between longitudinal bars, the minimum, okay, so this is actually the minimum requirement, is defined in terms of the value 150 millimeter or 6 inches. So it simply means that my clear, okay, if I take a look at my drawing here, my clear spacing is this one. Spacing of the vertical bars is must not be less than or must be greater or equal to 150. Okay, so that's your spacing. SC. Okay, so sorry class, I think there's some error here. So the clear spacing must be greater or equal, not uh, okay, so I'm sorry. So this is not a minimum spacing class. This is actually a maximum spacing because what we have here on top is already the minimum spacing. So the vertical spacing of lateral ties. So this is now the clear spacing between the longitudinal bars. So this is actually less than or equal. So this is checked. And therefore, this is not a minimum requirement, but this is a maximum requirement. Okay, so let's check our note here. So this must be less than or equal. So the reason for that class, we cannot exceed 150 or 6 inches because what we want to guard against possible bending of this. Now, so we don't want the stirrups like this, okay, to bend in such a manner that it will reduce, okay, it will bend like this. Okay, so we don't want to lose confinement of this layer, of this stirrup on the layer because the tendency for the particles here will be bursting outwards, okay? We'll push it laterally. That's why we have to limit our um, the clear, okay, the clear spacing between longitudinal bars, okay, or the main bars. Okay, so these are just a few of what we need to take note on. So on the next video, I'll be giving you a simple problem on how to compute for the safe ultimate load, the spacing, the minimum clear cover, and the clear spacing between longitudinal bar. Okay, so I'll see you on the next video.